Okay, so in section 13.1, we're going to be discussing vector fields. And vector fields are representations of vector valued functions in space. So you're already familiar with functions and vectors, and so we're just kind of combining those two into a way to represent functions that are vectors. Vectors have both magnitude and direction in general, and so a vector valued function is going to have both magnitude and direction, and because it's a function, it's going to be defined at every point x, y, z in your xyz plane. So an example of a vector valued function would be something like wind flow. And I've got a picture here for us to kind of talk about that. And you're actually already familiar with one special vector valued function, which is the gradient. We covered the gradient earlier in class. That was a vector, and inside it were functions of x, y, and z. So it was a vector valued function. But to think about wind flow, I'm going to sort of sketch out this picture right here when I'm talking about how we graph a vector valued function. So graphically, we represent vector fields as little arrows that we plot at every point in our three-dimensional space. And the base of the arrow, sort of on one of these arrows, like right here, is going to be the point xyz. And then the magnitude of the arrow, as well as its direction, is going to come from the definition of the vector valued function given by capital F, which can have components in the I hat, J hat, and K hat that we'll just denote as A, B, and C. And in particular, that magnitude, is going to be graphically represented as a length. And eventually, the reason why we're covering vector fields right now is that we plan to integrate over this type of mathematical object. So looking at this picture of a snapshot around Lubbock of wind flow, you could think about this being somewhere that we plot a vector field. And in this example, I'm actually only doing it as a two-dimensional vector field of y, and in this direction could be x. But then at any point on this coordinate quadrant, we could have a given x value and y value. So that would be the xy for this part of the vector field. And then from that point, we would draw an arrow with some length and direction. And so maybe it's super windy in Lubbock, the arrows are bigger there, it's a stronger wind flow, and maybe it's a little bit less windy over here in Fort Worth. The arrows are shorter and point in different direction because wind doesn't go the same direction everywhere. And so once you fill in all these different arrows all over the place, that generates for you an entire vector field. And I'm not going to highlight all those, but if you've seen a picture like this, you've seen a vector field. And so when we're working with vector fields, we're going to have a few important operations that we need to be able to calculate. Sorry, I need to change back to the pen color that I was using. The first is going to be denoted by this div f right here, and the way we calculate it is as del.f, where del, I'm just going to fill it in right now here, is the del operator, which you may or may not remember from us working with it earlier in the semester. I guess I'm going to write del operator bigger. When I made this, I thought that that would take up more space, but I was wrong. Okay, so div f is del dot f. It's a dot product between this vector of derivatives and f equal to abc. And so you're actually just going to get d dx times a plus d dy times b plus d dz times c. So for that dot product, I just calculated it the same way we learned at the start of class. I took first component here, multiplied them, then added second component times second component, and then third component times third component. And you can denote that as div f or del dot f, and in words, this is the divergence of the vector field f. The second operation we need to be able to calculate for vector field is what's denoted by curl f. That's del cross f, so this is going to be a cross product. And I'm going to write the formula here, and then if you're more comfortable with the determinant way of cross products, that's how I'm going to show it to you in the example. So when you compute this cross product, you're going to get dc dy minus db dz, and then dA dz minus dc dx, and then dB dx minus dA dy. So if you want to just write down that formula and plug it right in, if you're not familiar with determinants, that's going to be the way you compute this, same as you computed cross products. If you prefer to directly compute the cross product, you can do it that way instead. And this object is called the curl of the vector field f. And then just as a reminder, we also use this del operator to calculate gradients, which we denoted by del f. So it's that exact same thing you use to calculate a gradient. We just now combine it with dot and cross products because we're combining it with a vector, capital F, whereas before we combined it with a scalar, lowercase f.